all and welcome to this lecture. We are in module 8, lecture number 4, that is carrier velocity saturation part 2. In this lecture, we will see how we can calculate VDS dash, which is a point we decided which decides the saturation and non-saturation boundary, and we will see how the saturation to non-saturation transition occur when the velocity saturation effect is incorporated in small devices. These are the learning outcomes of this lecture, which helps you to understand how the velocity saturation or the carrier velocity saturation affects the drain current. It also affects the non-saturation to saturation transition. This will also help you to understand how we model the effective carrier saturation phenomena in MOSFETs. So, let us see a quick recap. In a previous lecture, we have discussed about the velocity saturation. What we said is, when the channel length is short enough, then the horizontal field, which is nothing but Ex, is very high, which can be given as VDS divided by L, and hence the velocity of the carriers are no longer linearly related with Ex. It means Vd is not directly proportional to Ex when the Ex is high. So, it will get saturated to its maximum value. We can simply say this is the curve where we define this point as critical field, this is Ex axis, and this is Vd max. By incorporating this effect, we said that now the carrier velocity is no longer linearly increasing, but it is getting saturated at that point. So, we need to incorporate this effect in our basic equations, and we did some calculation by considering a basic model of drift velocity as Vd max into Ex divided by Ec divided by 1 plus Ex divided by Ec, where Vd will be Vd max when Ex is greater than critical field, and Vd will be equals to mu times of Ex when Ex will be less than critical field. So, by doing this, we have extracted what is the drain current equation in non-saturation with including velocity saturation. So, in the non-saturation condition, the drain current equation with the velocity saturation equation was given by this, where this equation in the numerator we have already calculated. However, there is an additional term of 1 plus Vds divided by L into Ec is due to velocity saturation. So, now let us see how can we calculate Vds dash including velocity saturation effect, where we have already defined that Vds dash is nothing but a voltage value where the transition from saturation to non-saturation or from non-saturation to saturation occur. In our classical definition, we define this value Vds dash as dIds divided by dVds is equals to 0, meaning when the slope of drain current with respect to drain voltage is equals to 0, we define that value is as saturation boundary from where the current enters from non-saturation to saturation region. So, we will do the same thing here, and this equation is for the current equation, which can be given by W divided by L mu into Cox dash into Vgs minus Vt into Vds minus alpha Vds square divided by 2 divided by 1 plus Vds divided by Ec into L. So, this is the current equation when the velocity saturation phenomena is included. Now, let us do the differentiation delta Id divided by dVd or dId by dVd s and equate it to 0. So, we are doing the differentiation as denominator 1 plus Vds divided by Ec into L into differentiation of numerator W divided by L mu into Cox dash into Vgs minus Vt minus this will give you alpha into Vds minus numerator W divided by L into mu into COX dash VGS minus VT into VDS minus alpha VDS square divided by 2 multiplied with the differentiation of denominator, which will give you 1 over EC into L, and obviously 1 plus VDS divided by EC into L whole square. When you equate to the 0, you will ultimately get this factor will go 0 or cancel it out, this will be 0, and hence you will get 1 plus VDS divided by EC into L into VGS minus VT minus alpha into VDS minus VGS minus VT into VDS minus alpha VDS square divided by 2 into EC into L divided by EC into L is equals to 0. So, if you solve it further, you will see that VGS minus VT minus alpha into VDS plus VGS minus VT into VDS divided by EC into L minus alpha into VDS square divided by EC into L minus VGS minus VT into VDS divided by EC into L minus alpha VDS square divided by 2 into EC into L is equals to 0. So, this term will get cancelled out, and here it is half, here it is 1. So, ultimately you will get it as alpha VDS square divided by 2 times of EC into L with a negative sign. So, I am just multiplying with the negative sign also, plus alpha into VDS minus VGS minus VT is equals to 0. So, we will get a quadratic equation in terms of VDS square plus 2 into EC into L into VDS minus 2 into EC into L divided by alpha into VGS minus VT is equals to 0. We can solve this quadratic equation as VDS is equals to minus EC into L plus and minus square root of EC square L square plus, now it becomes 2 EC into L by alpha VGS minus VT, correct. Now, shall I take a positive sign or negative sign? Here I have to take positive sign, because if I take a negative sign, the VDS will become negative, and for NMOS, which we are considering here, the VDS cannot be negative, and hence we need to take a positive sign. So, here you take positive sign and take minus ECL out. So, in the left hand side you will get VDS, take minus ECL out, you are left with 1, and as you are taking positive sign, inside the bracket you left minus, and here you will get 1 plus 2 divided by EC into L into alpha VGS minus VT, correct. We can use a rationalization here, just multiply and divide by a factor 1 plus e to the power 1 plus square root of 1 plus 2 divided by EC into L into VGS minus VT divided by alpha, and in the numerator you will get minus EC into L. If you multiply it with 1 plus square root of 1 plus 2 divided by EC into L into alpha VGS minus VT, it is A minus B into A plus B will give you A square minus B square. So, minus 1 minus 2 divided by EC into L into alpha VGS minus VT. So, when you open this will cancel, and when you open the bracket, this minus and minus gets cancelled, ECL will get cancelled. Ultimately, the final value of VDS dash is equals to VGS minus VT divided by alpha into 2 divided by 1 plus square root of 1 plus 2 divided by EC into L VGS minus VT divided by alpha. So, this is clear that when you include the velocity saturation effect, then the saturation voltage, which decides the boundary between non-saturation to saturation, is lower than the boundary what we have calculated when velocity saturation was not included, because at that condition when the velocity saturation was not included, Vds dash was nothing but Vgs minus Vt divided by alpha. However, here we do have some factors which is actually gives you the lower value of saturation value. But strictly speaking, that the transition from non-saturation to saturation is not that sharp what we actually appeared, or that what we actually got in long channel devices. The transition from non-saturation to saturation, it will be smooth, right, when you include the velocity saturation effect. That's what we will see in coming slides. So now how can we include the effect of normal electric field? So whatever we have done so far, we have only talked about EC or EX, right. What EX is the electric field along the x direction or just parallel to the surface, but there is also provision to include the vertical field, because the carrier is influenced by the vertical field also. So to do so, we can incorporate mu effective, because we have seen that in mu effective we can incorporate the impact of vertical field as a theta into Ey effective, correct. So when you need to model a particular equation incorporating all the phenomena together, then you need to incorporate vertical field using mobility models and horizontal field using velocity saturation model. It is very important to note here that whatever be the short channel effects we are discussing here, they will come all together. It is not like one phenomena is occurring at a time. However, for the sake of simplicity and better understanding, we are considering all these short channel effects separately, but when the device will operate, all the short channel effects will come all together. So the impact which we will see at the output in terms of current, that will be the overall output of all the short channel effects. Now in general what happens is, we use this model, a more concrete model for velocity saturation. What we have used till now is Vd is equals to Vd max Ex by Ec divided by 1 plus Ex divided by Ec. That is what we have used, and ultimately we have ended up with equation as IDSN is equals to W divided by L mu into Cox dash into Vgs minus Vt into Vds minus alpha Vds square divided by 2 divided by 1 plus Vds divided by Ec into L. However, to get more concrete or accurate results, we need to use this model which says that this is power of n 1 by n. In general, for holes n is equals to 1, and for electrons n is equals to 2. So if you use n equals to 2, as we are discussing about the velocity saturation phenomena in NMOS, where the electron is a dominant component or dominant charge carrier, then you need to take care 2 here, and as it is 1 by n, so 1 by 2. So again, to calculate the same non-saturation current equation considering the velocity saturation effect, you need to use this model and do the same mathematics what we have done in last lecture, and you will ended up with this equation. So instead of 1 plus Vds divided by Ec into L, in denominator you will get 0.5 into 1 plus square root of 1 plus 2 times of Vds divided by L into Ec to the power 2. This is more accurate expression we need to use for our model. Now instead of having accuracy, I mean apart from the accuracy, this model is also solve the convergence issue. I will explain you how. Suppose you are using this model in your TCAD, then this model should applicable for PMOS also, as we have already discussed that PMOS is nothing but a flipped polarity transistor in comparison to NMOS. So if you use a negative VDS here, this model should be operated and should give an accurate result. So we can simply use mod of VDS for both type of the transistor. However, when you go for first order derivative or second order derivative of these quantities, then this model fails. This model will give you a convergence issue, and in analog basically these first and second order derivatives are very useful. So when you are going for a circuit design basically for analog circuits, then it is preferable to use this kind of model instead of using this kind of model. So this model will give you an accurate result. Second thing is, this model will solve multiple convergence or numerical issues. Now let us talk about the non-saturation to saturation transition. In last few slides we have calculated that what is the VDS value when you include the velocity saturation, but the physics behind calculation of VDS dash by just making the slope 0 dID by dVDS was as follows. What we said is, if we do have source and drain, when you increase the drain voltage, along the channel the charge will be tapered, right. It means near the drain the charge will go to its minimal value, and exactly at the drain end the pinch off occur and the inversion charge should go to 0. At that condition the drift velocity should go to maximum, or it should go to infinity to maintain a constant current, right, because the current is nothing but W into minus Qi dash into Vd. This was the basis with which we started our analysis without including the velocity saturation, and then we derived this equation considering that the slope of the current is almost 0, and this was the basis to calculate VDS dash. However, when we talk about the velocity saturation, as we have seen, the velocity of the charge carrier will not infinitely large, correct, and hence the velocity of the charge carrier will get saturated to its maximum value. Now what will happen if you increase VDS here in the drain end, the velocity of the charge carrier reaches its maximum value. So Qi dash or the inversion charge will not go 0, ultimately it will go to its minimum possible value, and this transition to reduce the Qi dash and to increase the Vd dash is very much gradual, in the sense the Qi dash will decrease and Vd dash will increase and ultimately gets to saturate such that the product remains constant, and this is a gradual phenomena, and hence the transition from non-saturation to saturation is very much gradual when we talked about the velocity saturation phenomena incorporated in our model. This is the reason it is really not important to find out a distinct value of VDS dash, right, because the transition is very smooth. Now if we include these phenomena in our models, like what we have derived as IDSN with velocity saturation is equals to IDSN without velocity saturation divided by, suppose we are using that model which gives you this factor in denominator. So ultimately you are using 0.5 into square root of 1 plus 2 divided by L into EC into Vd square, right, that is what here, correct, VDS by LC square, sorry. So it is VDS divided by LC square, 2 is out. So if you use this model, ultimately you are incorporating this thing in your modeling approach, but make sure that this modeling approach or model should not affect the weak inversion current transport, right, or the weak inversion modeling. Why? Because in weak inversion the carrier diffusion is not dominant, and hence suppose if you define a model, for example this black box is your model, and in this model you included a velocity saturation component that is, let us say, given by 1 plus velocity saturation. So this is a whole model, this is a complete model for all reason of operation, but this factor will actually disturb the weak inversion modeling. So, what is the approach? The approach to make a concrete model is, instead of modeling with respect to terminal voltage like VSB, VDB, we should model in terms of surface potential. This will give you a solution, as in if the model works in strong inversion, then the terminal voltages is exactly equals to surface potential, which is nothing but phi naught plus psi S0, and VDB is equals to phi naught plus VDB, or psi SL, correct. However, when you go for a weak inversion, then ultimately you will get psi SL minus psi S0 is approximately equals to 0. So, there is no current flow. So, ultimately the role of this next block will be cancelled out when you operate the device in weak inversion. So, the suggested idea is to use the model in terms of surface potential instead of using terminal voltages when you want to include the velocity saturation in your existing model. The next is, let us see the output characteristic with velocity saturation, how this output characteristic changes. So, this characteristic is plotted for a long channel device, and this is plotted for short channel devices, considering the velocity saturation effect come into picture. If we closely monitor these two graphs, we will observe few things. First, the saturation point, what we called is as VDS dash, it is shifted to a lower value. Why? Because we have already derived that VDS dash is equals to VGS minus VT divided by alpha into 2 divided by 1 plus square root of 1 plus VGS minus VT divided by alpha into 2 divided by EC into L. So, the saturation point is shifted to the left side. This is a point number 1. Point number 2 is the spacing between the curve is no longer square times, it is not quadratic, it is almost linear, and we have already seen that even if you are not including velocity saturation, because of mobility effect, because of source and drain resistances, this spacing is become linear, which is almost VGS minus VT. We can also justify this by including velocity saturation. In general, if you write a current equation, this can be given as W into minus of Qi dash into Vd, and we said that when you are talking about velocity saturation, then this Vd should not be replaced as mu into Ex, because this Vd is nothing but what? Vd max. We can simply say the carrier reach its maximum velocity, and hence if you write the charge equation, this will give you minus Cox dash Vgs minus Vt. From here also it is justified that current is no longer square dependent with respect to Vgs minus Vt square. So, the spacing is also reduced. The third point is the transition. If you see, the transition from non-saturation to saturation is very much smooth, and there is no distinct point with which you can decide that this is a non-saturation region and saturation region, right. So, and the reason which we already discussed, that always the carriers will try to get the product of Qi dash and Vd to be constant, and this process is very much gradual. So, let us see how my drain current is getting affected when you incorporate the velocity saturation effect. We are assuming that at V equals to Vds dash, my velocity saturation occur, and as I already pointed out, for velocity saturation effect, that Vds is smaller than, or Vds dash is smaller than Vds dash of non-velocity saturation effect. Okay. So, we are considering that the current is getting saturated, right, at lower value of Vds dash. So, I can simply write Ids dash is equals to W divided by L into mu into, this is W divided by L mu into Cox dash into Vgs minus Vt into Vds dash minus alpha into Vds dash square divided by 2 1 plus Vds dash divided by Ec into L. Now, as Vds dash is very much small, you can ignore this factor. this VDS dash is the value where the velocity saturation occurs, right. So, we can ignore this factor and simply as L is very small, so this factor is larger than 1, and hence you can rewrite this equation as this. If you see carefully, the L from denominator and numerator will get cancelled. This is strange but true. The current is no longer a function of L. So, current is directly given as W into COX dash into VGS minus VT into mu into EC, where mu into EC can be defined as VD max, right, or you can simply write VD max, where the velocity saturation occur, right. This can also be justified as, if you talk about the channel where this is n plus, this is n plus, and the channel starts from 0 and go till L. The transit time of the carriers, it means the time taken by the carrier to move from source to drain is tau, which was given as L divided by VD max, correct. And we said that the carrier velocity is getting saturated, meaning this factor is constant. So, the transit time of the carrier is directly proportional to L. And what about the charge? The inversion charge which are present here, it is also proportional to L. So, ultimately we can say the charge is also proportional to L. So, if you calculate the current under velocity saturation condition, it is nothing but Q divided by tau, and that will independent of L, correct. So, the current in that velocity saturation region will be independent of L. So, let me summarize here that we have seen the velocity saturation effect is a very important effect as a short channel effect, which we need to consider in our model. When we incorporate the velocity saturation, then the current equation can be given as IDSN divided by 1 plus VDS divided by EC into L. Later we said that this approach is not that good because it causes a convergence issue in simple CAD tools, right. So, basically we replace this approach as IDSN divided by 1 plus square root of 1 plus 2 into VDS divided by EC into L. The major takeaway of this lectures are, first, the transition from non-saturation to saturation is very smooth. Transition is very smooth. Second, the drain current is not a function of VGS minus VT whole square, it is a linear function of VGS minus VT. So, IDS is approximately a function of VGS minus VT. Third, the value of VDS dash when you incorporate the velocity saturation effect, which is lesser than the value of VDS dash when you not include velocity saturation. In general, the values of VD max for electrons and holes are equal. That is what I have showed you in previous lecture, that VD max value for electron is 8 into 10 to the power of 7 centimeter per second. In previous lecture, we have also discussed that the value of VD max for electron and holes are almost equal, which is 8 into 10 to the power of 6 centimeter per second for electrons and 7 into 10 to the power of 6 centimeter per second for holes. So, in modern devices, when the velocity saturation occurs, then the current of NMOS and PMOS are almost equal because of the velocity saturation effect. So, we will stop here for today. Until then, take care.